Now, as I said, the other source of magnetism within atoms is the atomic nucleus. We know now that, of course, nuclei are made up of neutrons and protons, and they form a little ball like this. The ball is very small, about 10 to the minus 14th meters across. Remember that the size of an atom is around 10 to the minus 8th or 10 to the minus 9th meters, right? So this is something like 1,000,000 times smaller than that. The nucleus of an atom is to an atom as, let's say, a grain of sand is to the volume of a cathedral or something on that order. It's tiny. It's a tiny, tiny, tiny little thing inside the atom. Nevertheless, we know its size quite well by measuring it, by shooting particles at it and so forth. And it's charged, it's positively charged, and it's spinning for sure. So therefore, it does have a magnetic moment. Every atomic nucleus is like a little magnet. And this is the basis of nuclear magnetic resonance. Now, back in the 80s when these machines first came out, they called them nuclear magnetic resonance imaging machines. And trying to persuade people to put their head in a nuclear machine was kind of difficult. So the language police said, let's drop that nuclear thing from it, because we're not nuking the person when they go inside here, right? All you're doing is putting their head or whatever other part of your body, their body you want to image inside this magnetic field created by, yeah, you got it, a big solenoid. The solenoid is wound with many, many turns, and it's superconducting, so you can get a lot of current going through it. And that creates a very strong magnetic field pointing in the axial direction of the solenoid, as we saw on previous slides. Okay, so if you're a patient and you're lying there inside this machine, what's it actually doing? All right, they turn on the magnet. That creates this very strong magnetic field that tends to line up all the nuclei in the same direction. So they're all pointing the same direction. Great. Now what? There are other coils inside there in 3 dimensions which can adjust in a fine way the shape of the magnetic field so that it has a particular value at a particular point in 3-dimensional space there. Okay? And then they put pulses on yet other coils which create a little radio frequency energy. And what that does is to flip the spins of certain nuclei around. And then they wait for sort of an echo pulse to come back from the nuclei when they all line back up again. That happens for only certain atomic species. So you can tune the machine to listen to, let's say, I don't know, phosphorus or calcium or some other type of atom at that 3-dimensional point in space that you're interested in. So by the strength of the returned signal, you have a measurement of the density of that atomic species at that point in 3-dimensional space. So under computer control, then, that imaginary point is moved around in a raster scan in 3 dimensions and maps out the density of calcium or phosphorus or whatever other material you're interested in inside the patient. Now, there's a really nice picture here showing the fantastic resolution and detail that you can get with MRI, magnetic resonance imaging. This happens to have been a magnetic resonance image of a guy who created the machine that he was willing to put his own head in there, so I guess it's okay. And it shows the inside of his brain, the structure of his brain. I don't know exactly which atomic species he's looking at, but it shows where it is in 3 dimensions inside the brain. Now you can obviously use this to study, look for an aneurysm or a tumor inside the brain and locate it very precisely. And the great thing about MRI is that it's non-invasive. All you're using is electromagnetic fields. You're not using any radiation. It's not X-rays. It's not gamma rays. It's not ionizing radiation. We're going to learn in the next couple weeks about, in the lectures on quantum mechanics, that certain kinds of radiation can cause electrons to be kicked right out of atoms, okay? In this case, you're not doing that. All you're doing is using the radio frequency energy associated with the magnetism of atomic nuclei and mapping out for particular atomic species where it is in 3 dimensions down to the sub-millimeter level. It's an amazing technology. We didn't have it 40 years ago. Started being developed 30 years ago, and it's been greatly enhanced since then. And we can use it for all sorts of things, including measuring in time what happens. That's called functional MRI, and they can use it to study brain activity, changes in the brain during things, and they're learning a great deal about the human brain and how the brain works by studying how it changes in time with in response to different stimuli.